Okay. So, going to take a quick little intro into thermochemistry or thermodynamics, which is our last chapter we have to get to. So, if you guys want the really intro version, I could get my son's Thermodynamics for Kids book that we can start off with. It's a cute book. It's like the series of science books for kids. They have like, string theory for babies kind of thing. They're pretty cool. They're pretty cool books. So this chapter, we're looking at something kind of different from what we've looked at before. In this case, we're looking at energy, and how the energy transitions around a chemical reaction. Okay, so some of our first things we're going to have to calculate. Like I said, this chapter or this test is going to be heavy in equations, so you will have an equation sheet. Okay, I will probably post up the equation sheet that will kind of give you a guide as to which equations you need to be able to do. So energy, heat, and work. So these are different terms that each individual one has its own equations. They have different signs. So that's going to be one of the reoccurring things that you see in this chapter will be the introduction of signs like positive and negative that are going to be directionally dependent. Okay, so oftentimes the questions are going to leave off positive and negatives, and they will rely on you to assign positive and negative when necessary. Okay, so that's kind of how they make it difficult in some problems, is by leaving off the sign and then assuming as it says heat is given off that you understand that that means there's a negative value. Okay, so being able to identify and assign signs for Q and W. Q is heat and W is work. Being able to calculate internal energy given heat and work. Again, there are relationship equations between these various things, and so we should be able to calculate these various terms. Energy and enthalpy should be able to calculate pressure, volume, work. So again, work is its own equation, so we should be able to calculate a work value. A lot of times these are examples that look like a piston, so it's a piston or a balloon, because it relies on expansion and contraction of volume in order to do work, which again, we'll talk about here in a minute. Specific heat, so we should be able to use specific heat to determine changes in temperature. Okay, so again, how much energy we put into a system will affect how much temperature it changes, how its temperature changes. You should also be able to calculate the heat required to change temperature. So if we know what the substance is and say, I want to know, how much energy is required to boil water, right? Which is a fairly substantial amount of energy. And especially if we're thinking about things like, okay, our world's water problem, right? Where we are eventually going to have, if not already, within the next generation or so, a severe issue of clean drinking water. Okay, many countries already have faced this kind of issue, whereas we don't yet. But one of the common ways that this is often dealt with is things like desalination. Like, how do we get clean drinking water from the fact that our entire planet is made up of water? That we have an ocean full of water, but we can't drink any of it. So how do we get the salt out of there in order to make drinkable water? And one of those ways is things like distillation, where we boil it, we get the water off, we leave the salts behind, but that creates a secondary problem of how do you boil water, right? And if you're living in a third world country where energy sources are scarce, as many other resources are, what resource are you going to use to boil water, right? It's not like they have oil, right? They don't have oil to do that. So, and if we're concerned about climate change, where's our energy coming from, right? So we're burning one resource in order to create another resource, while also then killing us with the first resource instead of letting us die slowly from lack of the second resource. So it's like a pain cycle of just creating a problem that fixes this problem, that creates this problem, that fixes this problem, and we don't actually make any real progress, right? So being able to calculate the amount of energy required for a particular reaction is an important kind of thing that we have to be able to do, right? Enthalpy of reactions. There's a little bit of stoichiometry left in this chapter. So our kind of stoichiometry process flow chart, I'll add another little notch into this. It's not quite as complicated as the other chapters because it's only really 2 steps. There's really 2 basic steps and 2 basic ways that the stoichiometry gets asked, but it really depends on, if you have this much fuel, how much heat is it going to produce? Or if I have this much heat, how much fuel did I start from, right? So it's treating the heat as a product, but we're not measuring the mass, of it. So it's only really 2 steps, right? And then should be able to calculate, enthalpy, which is delta H. We'll get all of those later using Hess's law. So Hess's law is kind of an important part of the chapter. We'll probably wait till next time to get to some of that. Again, we'll probably just do some introduction here to some of the terms and some of the equations, and then get into more of the complex ins and outs of the various problems next time. All right. Thermodynamics is one of our main topics of chemistry, and it's a major driver for pretty much everything that we do on Earth. We as organic beings, our sun is our primary driver of energy on our planet. It drives almost all of our chemical processes as far as biological life goes. So, this is kind of how the introduction, for kids goes, is, the sun, gives energy to the plants convert sunlight through photosynthesis into energy, which allows it to grow fruit. And then the conversion of energy through photosynthesis creates this thing. We eat the apple, converting the apple's energy into our energy. So it's an energy conversion process by which, the energy is conserved through these processes, but it's, it just changes form, right? It changes its form, but it's still the same energy. The same energy from the sun went into making the apple that goes into us, right? And so it's a constant fight against entropy. Okay, our bodies are a constant decay of energy. So our consumption of resources is really a biological fight against entropy. So we have throughout this chapter, we have things like, we'll look at, energy conservation. Okay, so when we have things like, obviously right now it's less of a problem, but like in the summertime, when I'm going to be sitting here in my office lecturing, and I'm on the 3rd floor, so I'm in the warmer part of my house, right? And so insulation and things are important in order to keep cold air in, or keep the warm air in. And so we, again, consume less resources as we build our houses more efficiently. And so we work on more efficient materials. And so, the energy transfer process in our houses is something that is applied to our various things in this chapter. So if we think about, like we talked about the noble gases, right, as insulators. And so when we have things like your double pane windows that are filled with an expensive like xenon gas or something like that, that creates a good insulation as opposed to a single pane of glass, it's not a great insulator. And so you reduce energy loss by insulating these processes. Same thing with like your water heater, right? So your water heater is constantly keeping the water in the tank warm, right? That's so that way you have warm water when you turn on the faucet. Or if you know, obviously there's other changes to this kind of system where it's like you have like hot water on demand kind of systems. But if you're not using that, then you know you've got a tank that's keeping the water hot. So, but it's always losing energy. It's losing some of that heat. So it's constantly having to put energy into the system in order to keep the water the same general temperature. So if you insulate the water heater, then it loses less of that energy, which means that it uses less fuel to keep that temperature the same, right? So there's ways that we can build efficiencies in our system to lower our energy consumption, improve our output and efficiency of energy loss and gain through a household. And so thermodynamics really begins to understand the difference in the movement of energy between different objects, whether we look at things like work, okay, which we'll talk about here shortly, but it can connect our whole scale of change in energy from very small molecules to very big systems. Okay, obviously your house is a very big system. Okay, much different than you know how much does it take to boil a cup of coffee, right? Or boil water to make coffee. So the same mechanics work on both of those scales. All right, so we should be able to identify and calculate Q and W as well as internal energy. Okay, so some basic definitions here. Energy is anything that has the capacity to do work or transfer heat. Heat and work are basically different ways that we exchange energy, right? So most of us, heat is going to be our most identifiable value, okay? It's a way of transferring energy, okay? Our bodies are always warm, okay? We are warm-blooded mammals, and so our bodies are warm because of the processes of our body are giving off energy as we consume things. And so we can, so like the emergency, you know, kind of safety stuff. If you're out in the cold, you've got hypothermia, you know, and you know, someone's there to rescue you, you know, you want to get down to the skin in order so that your body heat transfers your body heat to the other person's body, right? So that you exchange energy between objects. Okay. And so we have the same kind of dynamics as we do in physics when we're talking about this, is we have energy that goes through we see it in different forms. So we won't deal so much with potential energy, at least not in the same way that it's done in physics. So in physics, potential energy is an energy of height or position. So we don't really have height and position issues as far as chemistry goes, but what we do have are things like molecular bonds. So when we are eating food and our body, you know, we have some bar of how much energy we're using, and then, you know, the rest of our energy gets stored like as, an adipose tissue, as fat, right? So like when we're all sitting at home in quarantine and sitting around snacking all day long, maybe we need to put our mask on to keep ourselves from eating so much, but we're all going to have our quarantine weight we're going to have to burn off at some point, right? Because we're just consuming extra energy and we're not using it. Okay. And so eventually at some point when we need to get up and run, we can, those hydrogen carbon bonds are being broken down from the fat and they're turned into ATP, which then generates our energy, our kinetic energy for movement, right? So the kinetic energy is one that we will use more, just in the fact that we derive our primary unit of energy from the kinetic energy equation. Okay, so if you're not familiar with kinetic energy is 1/2 mv squared, so the mass times velocity squared. And so we generally get our SI units, kilogram, meters, and seconds as our units. So the mass and the velocity squared allows us to get a unit of a kilogram per kilogram meter squared per second squared, right? And so that essentially translates to a joule. So we simplify the kilogram meter squared per second squared to a joule, which is, I'm not quite sure why that's weird how that, okay. So looks like it gets cut off or something here. All right, so here you see it here. So 1 joule is a Newton meter. So a Newton is something from physics. So if you haven't taken physics, they talk about newtons, which is a unit of force, right? So when we get to work, okay, work is a force acting over a distance. So if I apply pressure and I move an object from one location to another, I'm applying a force and then moving it a certain distance. That's essentially what work is going to be. At least it is in the traditional physics terms, right? So a Newton is a unit of force, and the distance, which translates to a unit of joule. Or we can look at it from the kilogram meter squared per second squared, which is the kinetic energy value of energy here, okay? Or unit that we're going to convert to. So we boil it all down to a joule, okay, which is our unit of energy. Okay, we have a second unit of energy here called a calorie. Now, it's not, most of us are familiar with a calorie, at least in some ways, or at least we think we know what a calorie is. So a calorie is defined as the amount of energy needed to raise 1 gram of water 1 degree Celsius. Okay, so if I have 1 gram of water, how much energy is needed to raise its temperature 1 degree Celsius? And that value comes out as 4.184 joules. Okay, so it takes, that's how much energy is required to raise 1 gram of water 1 degree Celsius. Now, our dietary calories are not this unit. They're actually a kilocalorie. But because we're Americans and our system is, if it wasn't stupid before, we made it stupid and just changed it to a capital C calorie instead of saying it's a kilocalorie, because the metric system is scary and we can't possibly have that. So we just changed it to a capital C calorie instead. And so that is actually 1,000 regular calories. So if you're looking at your Snickers bar and it says you have it's 200 calories, it's actually not 200 calories, it's 200 kilocalories. Right? So if you're actually calculating down to the actual energy value, it's a kilocalorie. Okay. There's a kilowatt hour. We're not really going to use this, but it's in here. Okay. There's also a few other power units, but for the most part, we're just going to see things in joules. There probably won't be really any conversion of calories to joules. the unit conversions here, but I doubt we're going to do any actual conversions with that. So it's not quite like the gas chapter where we have a bunch of conversions that we have to do up front. All right. So one of the things that we have to take into account when doing this particular chapter are things like system and surroundings, okay? Because we have a transfer of energy going on, and that transfer of energy is always coming from somewhere and going somewhere else, and so we have to define what those somewheres are. And so we define them as the system and the surroundings. So usually, like if we're looking at this picture, the system is the chemical reaction. The surroundings are everything else, right? So if the chemical reaction is giving off heat and it's getting super hot, the surroundings are gaining heat and getting hotter, right? So the temperature of the surroundings are going up, so it is gaining that heat, okay? The system is giving off heat. Okay, so it's kind of like that oxidation reduction, acid base kind of stuff that we've talked about before. You have an equal and opposite gain and loss from physics, right? So if the system is giving off 100 kilojoules of heat, the surroundings are gaining 100 kilojoules of heat. Okay, and so there's always going to be this exchange between these two systems, okay, between the system and the surroundings, between these 2 points of interest. And so sometimes this is also important because we have to pay attention to the wording of the problems. Sometimes problems word things in a way that is slightly problematic and just meant to kind of throw you off if you're not paying attention kind of stuff, because they start suddenly talking about the surroundings, giving off heat, or the surroundings gaining heat, and it's not talking about the system, which is what you're using to calculate stuff from, right? So we have to pay attention to those things. All right, so some of this we have talked about before, okay? Law of conservation of energy. We talked about this probably the very first lecture, because I talked about the law of conservation of mass, right? Where mass is neither created nor destroyed, but we also have energy is neither created nor destroyed. So that means the energy we put into a system is the energy we get out of the system. So that makes some of the math, at least in some respects, a little bit simpler because it defines the parameters of our reality, right? I can't make new energy that wasn't there, right? So if I'm totaling up all my numbers, especially when we get to things like Hess's law, where we're looking at chemical reactions and you have multi-step reactions, each step just adds up to the total amount of energy, right? I can't exceed the total amount of energy, even if I take several steps along the way, okay? So first law of thermodynamics states that the energy of the universe is constant, okay? And like many other laws, this is a mathematical expression. This is a mathematical equation that defines an observable fact. Okay, so you're going to see some different things here. So let's talk about some of the terms here. The little triangles. Okay, these mean delta. Okay, so the delta means change. Okay, so anytime you see a little triangle next to something, that is the term delta, and it means a change. So when you're reading this, it says the change in the energy subscript of the universe is 0. Okay, there is no change. There is no change in the energy of the universe. So that means that the change in energy of a system plus the change in energy of the surroundings equals 0. Okay, so this means, or it should be obvious, that if my system is producing heat or producing energy, right, there has to be somewhere where the energy's, the surroundings are gaining that energy. And the terms, the symbols on them, positive and negative, one's positive, one's negative. So if it's giving off 100 kilojoules of heat, negative, there's someone else who's gaining 100 kilojoules of heat, is positive. So the summation of those, is 0. Okay. So also another thing to keep in mind here is that whenever we see the little delta, it is talking about the final value minus the initial value. Okay, so this is always what we see when we see the delta. All right, so you're going to see the delta a lot. All right, so you have to remember what this means. Okay, the change in whatever is it before. So if it's before the energy here, it's the change in energy, and it's always referring to a final minus the initial. Okay. All right, some other terms here. Internal energy is the total amount of kinetic and potential energy that the system possesses. Okay, so it's, again, it's not just internal, it's kind of just everything. It's the total value, it's the total amount of energy. And so you'll see this as E. Okay, so delta E is called the internal energy. All right, and so it is the final energy minus the initial energy. So every time we see the delta value, it is representing the final minus the initial. Okay, and because this is a value based on the final and initial only, it is called a state function. Okay, so it does not matter the process that it goes through. It does not matter how many steps it takes. It is only looking at the final and initial values of the system. Okay, so the way this is often described is this. Okay, if there is a direct path up a mountain, okay, it's usually probably not the easiest path, right? To take it directly, to go straight from the bottom to the top. A lot of energy. It's probably, I know, a lot harder because you have a lot of, vertical faces you got to get across. Versus if you take a windy path to the top, might be a little easier, right? Because there's probably like, little paths where you're looking at your vertical ascent, you're kind of breaking it out a little bit rather than trying to go a straight vertical amount, right? So the path here is longer for path Y, but it doesn't really matter. If one team took route X and one team took route Y, at the end of the day, they both made it to the top, right? I mean, both people would still be able to say, I climbed Mount Kilimanjaro, right? So it is only dependent upon the top and the bottom. The path does not matter in a state function. Okay, and this will come into play more as we get towards the end of the chapter for the Hess's law stuff. All right, let me move my. All right. All right, so we'll look at these last two slides here when we're going to look at the sign, okay? We look at energy as a diagram, okay? So here's internal energy. Here you have a final and the initial value. Okay. Mathematically, if we put this, if the initial value is 100 and the final value is 50, right? And it's always measured in final minus initial, 50 minus 100 is going to be a negative number. okay? So the negative here means energy is given off. If it's initially at a high energy and the final energy is down here, the energy had to go somewhere. Where did it go? Right? How did it get from up here to down here? Okay, so think of the example here as black powder. Okay, it's used in pyrotechnics. Right, it's not. I don't know if anybody uses it in gunpowder anymore. At least not exclusively, right? So it's probably more in pyrotechnics. All right, so the black powder is unstable, right? When it's ignited, it gives off a lot of energy. Okay. And at the end, it's this ash. Okay. There's nothing you can do with that ash. Okay. You can't reburn it, right? It's lost all of its energy. It is a more stable product. So it goes from a high energy product down to a more stable final product. Okay, we talked about this in the first lecture too, that things in nature tend towards they want to lower their overall energy. They want to be more stable. Lower energy means more stable. So in this process of being unstable and then wanting to become stable, it has to give off energy. So anytime you see something with a negative, okay, anytime you see something with a negative in this chapter, the negative sign means it's giving off energy, okay? Like the pyrotechnic. It is giving off energy, right? Like burning a fire, like burning a log, okay? That log, when you put a log in the fire, right, and you burn it, you can't get your log back, okay? It's giving off energy. The ash that it reaches at the end is a more stable product than the cellulose compound that it was made up of. Okay, so I got the last chart here. If the final energy is higher than the initial, the only way for the initial to get up here is for you have to put energy into the system. Okay, that's kind of so the example here is like the coal packs, okay, that our body heat is going into the system. We are putting energy into the system to raise its temperature. So our body's loss of heat is what makes it feel cold. Okay. Think of it also as things like boiling water, right? Or my boiling water example from before. If I'm going to boil water, I have to put heat into the water. I have to heat it in order to raise its temperature. Hot water has a higher energy than cold water. So I have to put energy in to the system. So anytime you see the positive sign, okay, whenever you see a positive sign in this chapter, we are putting energy into the system. Okay. I'm putting the Snickers into my mouth. Okay, it is going into the system. And then my body is giving off the excess body heat from burning that Snickers bar. Okay, negative out. My body heat is radiating out as I put energy in to my system. Okay. All right, so we're going to stop with that tonight. All right, so we're going to stop there.